When I first came to PARC, what, 7 years ago, I came as part of a language understander group. There were 4 of us, and there were soon to be 6. The only thing we needed in order to do some really exciting things were, well, the other 2 people. That didn't look as though it would be too difficult. And a nice programming environment, preferably that ran on the little personal computer under our desks and had a large address space. And due to some kind of law of conservation of useful things, we now have the programming environment running on the personal computer, and that's what we're going to see today. And as for the language understander group that was going to grow to 6 people, well, the only member of it that's left is having to moonlight now as forum committee chairman, and it may even go downhill from there. We have, as I say, a packed program, plenty of son et lumière. The son starts out, I understand, with Beau Sheil, and the lumière is going to come in the form of some demonstrations on the Dolphin machine, and at the end, a videotape. So, Beau.
For many of you, I think your association with Interlisp is restricted to the notion that it is the source of some of those ridiculous 15-pound manuals that you find distributed around being used as doorstops and other useful things around PARC. From that point of view, it would seem entirely appropriate that this particular forum on Interlisp be sandwiched between one forum on extraterrestrial intelligence and another one on nuclear warfare. I actually hope to convince you that that Interlisp and Lisp in general is somewhat more useful and more relevant to you than those juxtapositions would suggest. The first thing I should do is to mention that although only 2 names for typographical, logistic, and administrative reasons appeared on the announcement, this forum is really being presented by 6 people. Only 2 of us will actually talk today for limitations of time. The 6 people who put this together, the system and the forum, are those 6 names there, collectively known as the Interlisp-D group. We'd also feel only appropriate to acknowledge the fact that many, many people here in this room and elsewhere have helped us, both in the past and up till a few minutes ago. Given the aforementioned confusions, I think it's only reasonable for me to begin by explaining what Interlisp-D is. Because I'm a Lisp hacker, I'm of course going to give you a recursive answer to that. Interlisp-D is an implementation of Interlisp for the Xerox D machine series, the Dolphins, Dorados, and so on. Interlisp itself is a dialect of Lisp, and Lisp itself is a language which is the language of choice and the universal language used in artificial intelligence. For that reason, since the 6 names you saw flying by the screen a second ago are people who are normally included in what you call the artificial intelligentsia, and since Lisp is a language used for AI, we want one. And in order to see, we want one for a couple of different reasons. One is just simply historical inertia, like we've always had one, right? It's a good reason. Better reasons, or at least intellectually more respectable reasons, if not particularly necessarily more truthful, is this set of reasons. Lisp is a language which is designed for symbol manipulation. It was developed for that purpose as a mathematical representation for work in recursive function theory in the late 1950s by John McCarthy. And as a result of that, it has a very elegant basic semantics, and that elegant semantics has some ramifications as used as a programming tool. It has a very simple representation of programs, the same reasons again. And that means 2 things. Firstly, it means that program manipulation systems are very easy to write. And specifically, it means interpreters for special purpose languages are very easy to write. And that's one of the reasons why it's used in AI, because one wants to experiment quite often with the representational form of the programs you're writing. And having a language that gives you that flexibility is very important. Finally, because it has a single uniform data structure that forms the bulk of the representational mechanism in the language, it's very easy to build libraries and share code. So it's very easy to put stuff up together, put stuff up very quickly, share stuff very rapidly, in a very kind of loose and open style. That's the formal reason. Informally, or the result of all these things, depending on how you want to look at it, is this sentiment here, which Dijkstra included in his 1972 Turing address, that Lisp has assisted a number of people, a number of especially gifted people, in thinking previously impossible thoughts. It turns out it's also very good for the rest of us. Now, Lisp, unfortunately, is not a single homogeneous entity. It's a family of languages because of the number of years that it has been in existence. This genealogy, very briefly, to show you where we sit on that tree, Okay, the last common point was Lisp 1.5 in about 1962. Sometime shortly after that, MIT split off a family tree of their own, generally known as MacLisp and the MacLisp family. About the same time, BBN split off a different tree, the PDB-1 implementation, which went through a series of implementations of Lisp at BBN. That series stopped at BBN when most of that group moved out to PARC, where they still grace our corridors. And after some amount of negotiation, the name changed to reflect that fact, and it became Interlisp in around about 1973. At that time, around about that time, Peter Deutsch first started experimenting with the notion of a byte-coded Lisp. The notion being that you write a special-purpose microcode, as was becoming the style at PARC in those days, to implement a language, a machine language, so to speak, for the compiler instruction set for the particular higher-level language you wanted to implement. That notion, which he first published in 1973, carried on through a number of experimental systems in the Alto and the Dorado. And at about 1979, Interlisp-D, the successor of that series of systems, as a result of an attempt to re-engineer, redesign, performance tune, and extend that general design structure into a complete personal computing environment. Well, that's the genealogy of Interlisp. The question is really why we wanted Interlisp as opposed to the many other dialects of Lisp that are around. And there are 5 real reasons for that. 3 of them are kind of based, 2 of them are rather surface reasons, things you can just see by looking at the language, and 2 of them are a little bit more subtle. The obvious ones. The language itself. So I gave some reasons why Lisp is advantageous. Interlisp is really not all that different as a language from Lisp, except for some augmentations which make it into, in fact, a very much more modern language than its ancient origin would suggest. Reading that list of language features from the bottom, some of the things that are included in Interlisp are data types, the ability to define the way storage is handled and managed in a way that interfaces properly with the garbage collection and all that kind of stuff. Record package that allows one to write programs in complete symbolic representation-free fashion, if you choose. An Algol style syntax. It's a very bad choice of words. What I really mean there is the ability to use syntax for things like iterative statements, conditionals, and so forth, plus also infix if that really turns you on. And finally, the thing that's really different about Interlisp on a language level is a very prolix collection of stack features. Firstly, it's Spaghetti Stack, which was developed for Interlisp by Barbaro and Wegbright. And secondly, a very, very detailed set of functions to allow the user to get in and actually manipulate the stack. Now, approached from the point of view of conventional language design, those things look absolutely weird. And the reason they're in there, which is kind of very typical of the philosophy of Lisps in general, is to give people the ability to get in there and actually change the way the stack is laid out, alter almost every single part of it. And this has allowed people to build all kinds of tools that manipulate the environment. And once again, that's a very important general tenor throughout Lisp systems. The other thing about Interlisp, and the thing that really sets it off on a surface level from other Lisps, is a very extensive set of user facilities that take up about 10 pounds of that 15-pound manual that I mentioned before. That's a very 3 or 4 random examples, things like syntax extension, the ability to define new operators and things of that form. The whole mechanism of DWIM, automatic error correction, of which automatic spelling correction and automatic syntax correction is simply the most obvious manifestation. DWIM, for those of you who don't know, stands for do what I mean, occasionally pronounced do what Warren Titleman means, or what he thinks you mean. It's very easy to be flip about it, but it's a very useful thing. It eliminates considerable amount of stress and tension you feel when you make simple mistakes and nobody fixes them for you. And the final example of such a user facility is a programming assistant which keeps track of what you've been doing during the session, allows you to redo things, undo things, save side effects so you can't smash yourself or lose track of where you are too badly. Those are the obvious things. That's what Interlisp is known for. What Interlisp is less well known for, but I think is by far the best reason for it, are these 3 things. That is that what Interlisp really provides, and the thing that is the most significant contribution it's made, I think, to programming languages and programming environments in general, is that it provides an environment for experimental programming. And what I mean by that is an environment, a collection of integrated tools that allow you to write programs very fast. And the reason for that, which will become more obvious as we go through the forum today, is that most people who are working in Interlisp are experimenting with the programs they're writing. They don't know when they start out what they want. They're using the program as a way of refining their ideas. And so it's very important that they be able to move quickly while those ideas are still fresh. By the time they've got a design committee together, the ideas have gone stale on them. So we have this integrated collection of tools, and the way that in addition to the language aspects, the way these tools help is the fact that they provide a tremendous amount of bookkeeping support, which allows the programmer to spend his attention and energy on other things. Examples of those things: a file package. The file package is a completely automatic system of maintaining all parts of your source and data programs in terms of which files they belong to, whether they've been changed, whether they need updating, doing that so that, for example, when you want to go home, as for example to rush off to make a softball game, you just type cleanup and it's done. Somebody else keeps track of that, leaves some more neurons free for something else. MasterScope, a system which allows you to basically ask about your programs. At one stage, an example that we've used fairly heavily in talking about this system on the outside, we made a massive change to the internal structure of the I/O drivers of the system. We completely redesigned them. That was done without a single listing. It was done entirely by keeping track of where everything was by MasterScope. So that we basically asked who, anywhere, uses the record mumble. And it went and found all those places. And we said, well, edit in all those places. And it took the edit to every single place in the entire system. Okay. That kind of thing means that there's just one level of detail you don't have to keep track of. Finally, the structured editor, which is one of the oldest programming tools in Interlisp, symptomatic of a philosophy that now seems to be a little bit on the wane in the outside world, the notion of having an editor that really knows about the structure and meaning of your programs. That has some nice properties. The thing that's most important about it is the editor and the file package and MasterScope are all integrated together. So when you edit something, the file package knows about it. And so does MasterScope, so it doesn't give you the wrong answer that would have, that corresponds to the previous state of reality. Once again, this notion of the system intervening and taking care of you, removing some of the load from the programmer's work. Now, that style of system is all very easy to produce if you're willing to pay an arbitrary performance penalty for it. So the dual part of this, very important dual, is a set of what I've called contraction facilities. And we've been unable to get any particular agreement in this group on what the general name for these are. So this is my personal choice. The contraction facilities are ways of taking this program that you basically whipped out with these broad brush strokes and turning it back into the program you would have written if you only known what you were doing in the first place. Now, the most obvious component of that, of course, is a first-rate compiler, which is something that the Interlisp-D system has. It was worked on very hard for that reason. But more subtle things are things like an instrumentation package, so you can find out exactly where all the time is going. An ability to kind of compute the actual forms that are being compiled for any compile expression, so you can use declarative information or other things you happen to know to really tighten up a piece of code. And a very large variety of different means of providing declaration information to add to this knowledge base that's being kept by the system. So, for example, there's a type system which allows you to put declarations in your programs. There are all kinds of declarative information you can provide to things like the compiler in an attempt to squeeze the program down to reasonable efficiencies. And these techniques can be very effective if they're used well. And we find, for example, the Interlisp-D, to prelude a little bit of what will be said later, the actual operating system level of that system is actually written entirely in Lisp, and it runs perfectly adequately with no problem whatsoever. The final thing, the third of these so-called invisible aspects of Lisp is a very reactive user community. One of the things that's been tremendously useful for Interlisp throughout its 10, 12-year history is the fact that it's been working for a group of people who are programming language buffs. They're programming language buffs because a lot of what they're doing is writing special purpose interpreters for their own languages. So they're very highly motivated about the design of Interlisp itself. They care a lot. They argue, they bitch, they moan, they react. And the system has grown in response to that reaction. It's taken a tremendous number of good ideas from the outside and incorporated them in. And that's been one of its real strengths. So much for the motivation for Interlisp. In some sense, we had all of this on the PDB-10. What do we not have on the PDB-10? Why do we make Interlisp-D? Well, the leading answer is not what you might have guessed. The leading answer is the fact that we were running out of address space on the PDB-10. PDB-10 has 18 bits of address space. Around about 1977, for the first time, some of the large AI programs at BBN and other places started to bump into that limit. And that's a hard limit. And after a lot of squeezing and moaning and pushing a couple more bits out of shadow space, people realized that the PDB-10 was just coming to the end of its usefulness for large AI programs. At the time it was built, that 18 bits looked very large. At the time the initial designs of Interlisp-D were laid out, 24 bits looks pretty large. It'll give us a few more years at least. The second motivation for going to Interlisp rather than switching some other kind of Lisp, apart from the inertia and other reasons for maintaining the kind of environment that you're used to, is that we have, the group that was working on the system, a lot of outside collaborations with people at other sites, people at Stanford, people at BBN, people at RAND. And it's been very productive how we've been able to exchange code and ideas with those people over the years. We made a decision that we would stick with that we would go with Interlisp-D, we would try for exact compatibility so we could keep that up. And finally, of course, is the motivation that you would have expected from the top of the list, and that is that after a long period of time on a time-shared machine, we decided we really wanted to get involved in personal computing. We kind of hung back for 5 years, and it's obviously not a passing fad, and so we thought we'd give it a go. We wanted to try and marry a lot of the symbolic tools that Interlisp had developed, and in some sense, Interlisp had pushed the state-of-the-art in time-shared environments about as far as it can go into on a time-shared machine. And so we wanted to start marrying some of these strong symbolic and knowledge-based programming techniques to some of the interactive graphics and the techniques that have been developed here on the Alto. We wanted to work with distributed systems, so we wanted to basically get into the personal computing environment. So what we'd like to do now is, having told you why we started out down this path and what the kind of intellectual justifications for it are, we'd like to show you basically how far we've come. We've had about 6 months since the system first became equivalent to the PDB-10 system in reliability and speed, but with these graphics and network augmentations. And we'd like to show you now, Larry Masinter would like to show you the state of the current system and where we've been in 6 months from there.
Features of the Interlisp-D programming environment. And in order to illustrate some of the facilities, we needed to have an example program. So I'm going to take a program and change it. In order to show some of the facilities of the Interlisp-D programming environment, we thought that we would take a sample program running on the Dolphin here and make a small change to it in order to show how the tools in the programming environment enable this flexible style of program development. The program that we decided to use as an example was a thing that Ron Kaplan put together in his work on in linguistics, which was a editor for parse trees. And so here I'm calling the parse tree that calling the editor on a parse that he generated. And so he told me, well, I call edit tree and give it the sentence to parse, and that will let me open up a window, and you'll see down here there's the parse tree, and there's a little editor running in it, and you can pick up nodes and move them around, and has a little rubber band metaphor, and you can even do things like delete links or add new ones. And this was sort of like the application I had in mind, except that I really didn't want to edit lattices or trees, but I had an application where I wanted to edit arbitrary graphs. But if you look carefully, as I take this node and move it up to the top of the screen, you'll see that the line always really goes from the bottom of the from node to the top of the to link, and that's really unaesthetic, and especially if we added a lot more nodes to the network, that it just wouldn't look good at all. And so I'll take this. I wanted to take this program and make a small modification to it on to the way that it drew the links. Now, since I didn't know anything about the structure of his program, I first took Masterscope. I'll ask Masterscope to show me the call structure of the program. And so I say, show paths from edit tree, and the calling paths, it lets me open up a window down here, and as the window gets opened up, it will show this call structure. And oops, well, the window's not quite big enough. Let's draw it a little bigger and see how it looks. So I'll increase the size of that. Now, if you look at here, if you look at this tree, you'll see that at the very top is edit tree, and going down on the right, edit tree calls it calls edit lattice, and edit lattice calls display node and also closest node. And we can use this use this tree structure not only as a picture of the structure of the program, but we can also, when we point at a particular node, it will let us open up a window that will show it, in which we can see the definition of the function that I just bugged. And so here I've opened up a window, and it will show the definition of edit lattice, and I can go down and bug another function. I go down and oh, and that one looks nice. Display link, and that looks like this is the function which is actually drawing the lines. It's called the draw between line primitive between the from pause and the to pause. And if I go down and look at those, from pause apparently is doing a record access, just accessing the bottom of the node, and so, and likewise, if I go down and bug to pause, I can see that to pause is a record access. So the first thing I want to do is tell MasterScope to find the places where from pause and to pause are used, and expand them in line, since they're merely doing record accesses. So I tell it to edit where any calls either of those functions, and then you can do an edit command, and I'll use the command that says take the definition of whatever the function is and expand it in line. It's loading in the definition of display link and making the edits to those two places, and then and it's done. Now if I go back and tell MasterScope to show me the calling structure again, you see down at the bottom it called from pause and to pause, and when I tell it to redo the show, that those links are missing because MasterScope knew to reanalyze the definition before it tried to show the calling structure. And if we look at inside the definition of display link, we'll see that in fact those calls had been expanded. Now I want to go in and change the definition of display link, instead of always going from the bottom to the top, to do a conditionally draw from the bottom or the top, or from the left to right. And so we'll make a series of edits. I'll first embed this in a conditional that says if the from node's bottom is above the two nodes top, then I will go ahead and draw from the bottom of the from node to the two node top. But on the other hand, and I'll make the same condition except switching the roles of the from and the two nodes. And then I'll also do a similar tests with except changing from above and bottom top to left and left and right. One of the nice things that this interactive environment allows is that you can make changes and quickly see the effect of them, because as soon as I've made the edit, I can go ahead and try my parser again. I typed in redo parse, and in the history facility, the parse tree is popped up down here. And now if I pick up one of the nodes and move it around, you'll see that the links move to the appropriate path, although it prefers the top and above. And if I put one node on top of the other, then it doesn't draw any link at all. So having made our small edit, we'll now leave the system to amuse itself. So if I, all right, so. Well, thank God I made it this time. I think that's about it. Yeah, that there are, so we can stop out of the graph editor and show a few more things. I'm sorry, I can't hear you. Oh, this is running on a Dolphin. Oh, yeah. All right, this Dolphin right here. And so I suppose we do need to say this. This is not on a Dorado. The Dorados are, of course, 8 or 9 times faster, but there are not as many of them. So, why don't you lead into the video teaching?
Man of the flying fingers. I'm sorry for the video mix-up that caused the monitors at the back there to become very difficult to see, and the fact that Dick couldn't follow accurately for the same reason. I hope that gives you a flavor of the kinds of facilities we've added to this environment. You know, the use of graphics, which essentially plugs into the symbolic facilities were already there. And we'd be delighted to show any of and all of you much more of those over time if you want to come down and chat with us. To continue onwards, in order to kind of basically review our state and where we are in a kind of more abstract fashion, I'd like to basically start with project goals and indicate how far we've gotten, what our state is in terms of each one of them. So I mentioned before, it was very important to us that we be completely compatible with the PDB-10 in order to share code with outside users, to bring our own code over. We're very happy with that. We've reached the stage now. We actually reached the stage last summer where we can bring over huge applications programs from places like Stanford and just put them on our machines and they run. Okay, modulo their programmers having decided to, for example, execute 10x JSYSs. And that's a very high standard of compatibility. Occasionally it's heartbreaking when you go in there and you decide that some part of the design that was done in 1971 really just isn't done right. It's very easy to go in there and just start doing a little bit of designing on the fly. But we have really stuck very hard to maintaining a complete compatibility so we can, in fact, continue to draw on this outside research. That's very hard and very unrewarding at times. Excuse me. Performance. We were not willing to sacrifice performance to go to this environment. And what we've managed to do so far is to maintain the level of performance we had. Currently the Dolphin seems to run, although the profiles of the two machines are very different, Interlisp, but around about twice the speed it runs on a KA-10, which is the system it was originally designed for back in the 1970s. We still think we have quite a bit of room left in that machine. And the thing that's important about it is it's a very pleasant functional environment. I mean, you saw Larry hacking away there faster than Dick could follow him. And that's some kind of measure of how comfortable it is to work in this environment. Reliability didn't crash during the demo, did it? Transportability, not the next thing on my list, is another kind of issue that we've got real concerned about. This was a massive, massive effort. It's running over 2 years, several men. Most of us had to stop our research completely in order to get the system done. We don't want to do it again. And in order to not have to do it again, over the last year we've started to spend a lot of time going over the system and making it so it could be moved to another machine of this kind of class. And we hope that the Dolphin and Dorado are not the last machines that we ever have to work with. And when the next one comes along, we're going to be ready for it. Functionality was, of course, the critical issue that the demo addressed, that one of the kind of new extensions to take advantage of this environment. They're just starting. We've had the environment now for about six months, and all of a sudden things are starting to happen. These kinds of programs that Larry demonstrated begin to be very easy to put together. And we hope over the next year there's going to be a whole explosion of programs of that kind, making advantage of the interaction of the Interlisp environment, the Interlisp symbolic environment with the personal computing facilities. The last thing on this list of project goals really wasn't a goal when we started, but that was to turn this thing into a Xerox product. It seems to have happened along the way. As many of you know, recently XEOS, Xerox Electro-Optical Sciences in Pasadena, announced that they were willing to take orders for a Dolphin running Interlisp, which is in the course of being become an official product, has become the Xerox 1100 Scientific Information System. We did not choose that particular name, but the lawyers say it was the only name that was sufficiently vague that fitted into their product taxonomies. The current state of that actually grew out of the fact that a year ago, as many of you know, we held a very big open house here for members of the Lisp conference and the AI conference at Stanford. We had a lot of people come over here. They got real excited at the fact that all of a sudden there were wide address Lisps available on these small machines, and a lot of them said, gee, we'd like one of those. And so we said, sure, okay, we'll see what we can do for you. And we went away and talked to EOS, who were interested in doing this kind of work, because most of their work is government contracting, and they're used to dealing with small lot special kinds of operations. And they have now decided to offer this to the outside world. And the first machine, which has actually been ordered, will be placed at Stanford University in August to the cohorts of Dr. Feigenbaum over there. So we've come a long way in a year. In terms of where we're going, well, more of the same, obviously. More orders, more functions, quicker transportability, more reliable, running faster. But really, the important thing about Lisp is that what Lisp has always done, Interlisp, rather, has always done, is to grow in response to its users. And so if you really want to figure out where we're going to go, the best way I can describe that to you, other than give you a wish list of things I'd like, is to let you meet some of the people who are using Interlisp-D. And look at the kinds of projects they're doing, look at the kinds of things they're talking about, because it's in response to them that we expect the system will continue to grow.
This is one of the oldest puzzles known to man. It is the Towers of Hanoi, a puzzle which has been known in Southeast Asia since antiquity. It has almost as distinguished a history within the young science of artificial intelligence, as many of the earliest discussions of problem solving were carried out in terms of this ancient puzzle. For this reason, it was adopted as the logo of the Interlisp-D programming system, a system which provides Interlisp's symbolic programming power in a flexible, interactive, personal computing environment. To illustrate its range and power, we will review 4 significant applications of Interlisp-D, which exploit its facilities in characteristically different ways. One of the principal uses of Interlisp-D is in basic research on artificial intelligence. Typical of such applications is that of cognitive and instructional sciences visiting scientist, Stanford University professor Doug Lenat.
One of the most fascinating topics in computer science and artificial intelligence today is learning, the acquisition of knowledge. Sometimes that takes the form of transfer of expertise between some domain expert and a program. Sometimes that umbilicus is severed and it takes the form of a program being exposed to an environment about which it has to learn and form its own concepts. And it's that latter situation that I've been doing research on. Originally, about 5 years ago, I wrote a program called AM that worked in elementary mathematics, that started with about 250 heuristics, rules that guided it to perform plausible actions as it searched for interesting new mathematical concepts, gathered data about them, noticed conjectures involving them. The trouble was that AM's behavior began to degrade after a while. It was very exciting when it discovered cardinality and number theory, and eventually concepts such as prime pairs. But as it began to work on them, it began to thrash. Now, why was that? The basic problem is that this concept of prime pair is defined in terms of this one, which is defined in terms of this one, and so forth, down to a concept about which AM had a few heuristics. These few weak general set theory heuristics weren't powerful enough to constrain AM when it was working in number theory. So if you think of knowledge as comprised of facts, objects, operators, terms, jargon, textbook knowledge, and heuristics informal judgmental knowledge. The problem with AM was that it wasn't capable of discovering that second kind of knowledge. It wasn't capable of discovering heuristics. And therefore, we built a new program, Eurisko, with that goal in mind. The key to Eurisko is every heuristic is represented in exactly the same way as the mathematics concepts and the other domain-dependent concepts in the system, so that the heuristics operate not just on mathematics concepts and geology concepts and biology concepts, but the heuristics can operate on and modify and synthesize heuristics. That's the real source of power. Now, you might ask, how exactly do new heuristics come into being? You could imagine them coming by specializing some general heuristics that you have, or by generalizing, by compiling the hindsight you've acquired into new heuristics which, if only you'd had them sooner, would have gotten you to your current state that much faster. Or by analogizing, taking a look at heuristics from other fields and paths that you followed to get heuristics in other fields, and seeing if any of that carries over into the current situation. Now, the answer to this question is we don't know which of these methods is the most valuable, and we don't know exactly how each of these methods works. That's the reason why we've built Eurisko, an experimental vehicle, an Interlisp program that embodies these methods, that goes off and tries to discover mathematics concepts, occasionally abstracts from that experience new heuristics, and thereby beats this kind of thrashing problem that AM suffered from. Okay, without further ado, let's go over and take a look at the Eurisko system and see how it discovers new heuristics as it discovers mathematics and other concepts. The Eurisko screen is divided into several windows. Starting with the one on the right, we see the list of topics that Eurisko knows about, including mathematics, oil spills, programming itself, and under that, the list of tasks on its current agenda, tasks which are plausible, promising things for Eurisko to spend time working on. Moving to the left, we see the current task that happens to be selected and is being worked on, and below it, the heuristics which are being applied to that current task. Down at the very bottom, you see rapidly flickering numbers, which are the numbers of heuristics which are potentially relevant to working on the task. Just above is the English abbreviation for the heuristic which is currently firing. And off to the left is the concept which is being worked on. In the current case, you see that the concept is H1, that is itself a heuristic. So we have heuristics such as H4 being applied to other heuristics, in this case H1. Let's interrupt it and take a quick look at something it just did. In heuristic H12, in a slot called then compute, it changed an and to an or. H12 was a heuristic which said, if you've gotten into a bad situation, then create several new heuristics, any one of which would have been capable of avoiding the situation if only you'd had it sooner, and presumably avoiding similar situations in the future. What Eurisko has just done up here, by changing and to or, is to create a new heuristic, H12-1, which is very similar to H12, but instead of creating several such new heuristics, it will only create one new heuristic. It may very well turn out that H12-1 is a more useful heuristic because it doesn't create so many new ones. And if that's true, eventually H12 will be subsumed and destroyed. At the moment, Eurisko is executing a heuristic to see if any known heuristics are equivalent to H12-1. the new one it just synthesized. None of them are quite equivalent, and it accepts it as a brand new heuristic.
At the opposite extreme from Lenat's abstract symbolic reasoning application is the use of Interlisp-D as a flexible, interactive prototyping environment. These secretaries are operating a Xerox copier in an experimental laboratory where their behavior can be precisely observed. The research program of which this observation is a part is described by computer scientist Austin Henderson.
This is a Xerox 8200 copier. Our customers tell us that there are difficulties in operating it. The folks back in Rochester in the reprographics division who design and build these machines are also interested in those customers and the operability problem that they seem to be facing. They came to us because we're interested in understanding how people understand machines, with the question of how computer technology might be used to improve the operator interface to such a machine. This particular machine is here in our lab, where we can observe what people actually do. From those observations, we can design experiments to probe the structure of the problem solving that they're engaged in.
One of the most difficult things for an engineer to appreciate is the extent to which the logic of a machine is in fact not at all self-evident from the machine's design. The only way in which that logic can be discovered is if the designer very deliberately and very intentionally leaves signs for the user. One of the objectives of our observations is to see how it is that a user approaches the machine, what signs are in fact effective in conveying the machine's design and the designer's intent for how the machine is to be used, and what signs really are either too subtle or are overlooked, or alternatively, what signs are subject to so many different interpretations that it's just as likely that the user is going to hit on the wrong one as on the right one.
To support the experimentation with control interfaces, we decided to put together a prototype environment in which designers of proposed interfaces could mock them up and experiment with them to see what they're actually like and would actually be like in reality. What I've done here using my computer in my office and using the environment we've put together is actually build such a control interface. As on the 5700, we have a frame in which we can move off to various different modes. I'm going to move to the copy mode just to give you a sense of what you can put up. A set of buttons, a set of information which might correspond to what's on the flip card. As we get over here, there are various different choices, but these particular choices talk about the sidedness of the original and the sidedness of the copies. If I, in fact, push on this, notice what happens. There's a sudden interaction between these two because this machine won't allow you, it has no way of doing, taking two-sided originals and making one-sided copies. So when you try to get into that mode, it forces some other legal choice which does in fact involve two-sided originals. If, on the other hand, I try to go back, what we've given, just as a way of showing the capability of the environment, is the machine actually complaining audibly about what's going on.
Sorry about that. This machine has no simple way of making single-sided copies from two-sided originals.
Well, suppose that we want to explore this interaction between two different dimensions. I've set up an experimental frame having to do with the handling of constraints, in which I've put up various different ways that you might go about presenting the user with this constrained or interacting environment. The goal of the simulation is to provide the designer with the ability to try out choices like these quickly and easily while the ideas are still fresh in his mind.
Observation and prototyping provide one empirical basis for the design of the human interface to complex machinery. But for the development of a scientific theory of the way people reason about machines, we must turn to basic research in cognitive science, an interdisciplinary study of thinking that draws on the diverse disciplines of psychology, computer science, linguistics, and education. Typical of such research is the work of cognitive scientist Dick Burton.
One of the long-range goals of the Cognitive and Instructional Sciences group has been to develop a scientific theory of procedural errors or errors in procedural skills such as operating electronic office equipment or solving mathematical equations. From some studies that we did of students' procedural skills in mathematics, we discovered that a large number of their mistakes could be explained as modifications in the procedure. That is, they were not following the correct procedure, they were following their own incorrect version, which had what we called bugs in it, in order to study where bugs come from, what their structure is, and try to form a theory that might be abstracted into domains more complicated than mathematical skills. We set about to discover all of the bugs in subtraction. To do this, we developed a program, which I'll show you in a moment, called Debuggy, which takes a student's answers and derives the bug or collection of bugs which explain those answers as best it can. Using this program, we can take a collection of students and diagnose them, and those that are not diagnosed as having bugs we can look at by hand and see whether or not there are some bugs that they have that the program doesn't yet know about, and thereby increase the collection of bugs that we have. Using this procedure on several thousand elementary school students so far, we've discovered 130 primitive bugs in subtraction. In addition, we have discovered students with as many as 4 primitive bugs in their procedures of subtraction. What this means is that Debuggy has to work with a search space which is somewhere on the order of 10 to the 8th possibilities. A large amount of Debuggy's intelligence is embodied in heuristics for controlling the search of the space. In addition, we have the problem that students do make careless mistakes, that they will occasionally make fact table errors, and so that Debuggy can't rule out hypotheses just because it finds one instance that disagrees with that hypothesis. What I'd like to do now is turn and show you a little bit about how the program works. This version of Debuggy is set up to allow a designer of the system to play with varying strategies for controlling the search of the space. It's set up so that I have a menu up here that I can use to tell it what to do, or I can tell it to go ahead and choose on its own. The other information on the screen down to the left, we have the examples of the student's previous work, and below that we have current hypotheses that the system has and how well those explain the problems that have been done so far. In this case, we can see that none of the hypotheses being displayed have explained the student's problem. So I'll come back here and tell the system to go ahead. And what it will do, since it doesn't have any hypotheses that explain anything, is it will try and generate examples which evoke primitive symptoms by using primitive bugs to generate them. It has generated this problem, and I will solve that using the mouse to select numbers, and I will have it update the display of hypotheses that it has. And if we come down to the left and see that it stopped displaying all the hypotheses it had which didn't explain anything, and it now has one which is left justification, which does explain this one problem. System continues, and it tries to expand that hypothesis, which explains some of the information, to add primitive hypotheses to that to account for more information. If I update the display, we can now see down on the left that it has a large number of hypotheses that explain that one piece of information. In fact, it has a hypothesis which explains both of the pieces of information seen so far. Now, this hypothesis here explains the 2 pieces of information we've seen so far, but we can't be sure that it's in fact the bug the student has. The student may have made a mistake in one of the problems that we've seen, or the student may have a more complicated bug than that, of which this is a part. So the system will continue to look for more complicated hypotheses and continue to entertain the hypothesis that there might have been noise. Update the display. What the system did was to put together 2 more hypotheses in addition to the one that we had started, which are compounding the bug that it had before with new bugs, and ended up getting it 3 bugs which now explain all of the behavior so far. The system will now generate problems that split between those 3 bugs, that is to say, generate problems whose answers are different depending upon which of those bugs the student has. And at this point, after seeing 6 examples of the bugs with no disconfirming, the system believes that that's the diagnosis. There are several reasons why Lisp is turned out to be a good language in which to program debuggy. One reason is that the model we have of a bug in subtraction is a function, and Lisp is a good language for dealing with functional objects, so that we could model a bug as being an alternative definition of one small piece of the correct procedure, and then swap that in very easily, and this allowed us a nice natural way of modeling multiple bugs as swapping in 2 or more incorrect procedures. Another way that Lisp proved helpful was in terms of its ease of modification. This program has been evolving over the course of the last 5 years. It started when we knew about 20 bugs in subtraction, up to where we now know about 130. The heuristics that work when you have a search space of 20 bugs don't work when you have a search space of 130, and so the program has had to evolve drastically over that time. In addition, the structure of the program has to keep up with our understanding of the diagnostic process so that we can use it as a basis for developing further new ideas. So that our program.
This application, like Lenat's, draws mainly on the symbolic programming power, which has been Lisp's traditional strength. The enhanced personal computing environment is pleasant, but less significant to the research. However, in a joint project with Stanford University, Lisp's symbolic power is combined with Interlisp-D's interactive personal computing environment to explore knowledge-based techniques for the design of integrated circuits. Stanford University research associate Harold Brown discusses this work with Xerox scientist Mark Stefik.
The design of integrated circuits, particularly large-scale integrated circuits, is a very expensive process. The Intel Corporation recently announced a new 32-bit microprocessor, the 432. The 432 consists of a 3-chip set containing approximately 400,000 transistor sites. This is right on the border, the lower border of the VLSI technology. The Intel people estimate that there was over 100 man-years of effort that went into the design of this 3-chip set. Now, the implications of such a tremendous design costs are that there is almost no room for experimentation with alternative designs, with novel architectures, experimentation of any kind.
The Intel 432, which took over 100 man-years to design, is an example of why the design process is labor-intensive. We might ask, well, why is it so difficult to, what makes this so difficult? And the answer is that there are so many ways of looking at what a chip is. It has to have certain kinds of behavior, it has to fit in a certain way on silicon, it has to act as a digital system. We can think of the digital system in terms of voltages, in terms of certain kinds of behavior. And all of these things must come together finally in some physical realization which constitutes the design of the chip in the end. The way a designer can approach all of this is that he thinks about things incrementally. He tries to factor his concerns. He tries to work within certain kinds of methodologies that allow him to think about some part of how a chip works at any given time. One of the major interests of our projects is to understand how it is that a methodology organizes the design process, and how, in fact, the knowledge that goes into a methodology can be represented in the computer system. And this is, in fact, why we go to artificial intelligence.
Another important way that experienced IC designers manage the complexity of the design process is by applying a great deal of expert knowledge. That is, this knowledge can range anywhere from straightforward equations that can be used to compute, say, the pull-up, pull-down ratio of an inverter, all the way to very vague rules of thumb of how to place a certain type of component on the silicon. Another one of the major interests of our project is in capturing this sort of expert knowledge within a design methodology, representing that knowledge within the computer, and using it to amplify and assist in the design process. Now, for such an approach, one needs a mechanism for viewing and making modifications in the knowledge base. Now, what we have here is a very first-cut prototype of a knowledge-based design editor for circuit objects. The circuit objects and the relations between them are displayed in this editor via these block diagrams on the screen. One can peruse through this knowledge base by following the structural hierarchy relation. These block diagrams, as they reflect the knowledge base, are not arbitrary, but must obey about a dozen constraints, that is, rules. For example, a connection point where a communication line connects to one of these blocks must always be on the boundary of a block. The design editor is constructed to enforce that. We'll make one of these connection points, and as you can see, the design editor only allows the connection point to be in a legal position on the boundary. In general, the design editor enforces all of these these rules, these constraints, and in addition, it maintains the consistency of the relations between the objects in the knowledge base.
A knowledge-based design system has many components. In addition to facilities for browsing and changing the design, one must be able to explore its behavior.
On the Dolphin screen, we are now looking at an example of such a circuit, a synchronous active memory, or SAM for short. Each square in the figure corresponds to a SAM cell. A SAM cell is a simple processor with 16 bits of memory. The design problem was to design an appropriate instruction set for SAM. The kind of applications that we had in mind are image processing applications. An example of an image processing task is edge finding. We'll now look at an example of an edge finding program running on the SAM array. As the simulation proceeds, we see each of the cells exchanging information with their neighbors. The instructions that they are carrying out are being displayed in the upper left part of the figure. The calculation proceeds by first computing the interior of the figure and then subtracting that from the original, leaving behind the edge. Now, as that ran, we observed that each of the cells had to exchange information with neighbors in 4 different directions. It had to iterate through the same instructions for all of the 4 directions, and this led us to the idea of having a single instruction, a sort of 4-way fetch, for getting all that information at once. We then incorporated this new instruction into SAM, and we can now see another edge finding program which runs substantially faster. This version of the edge finder finds edges of an arbitrarily complex image as long as it fits inside the SAM array in exactly 5 cycles. It would have been simple to build a program like this, a simulation or animated simulation of SAM, had we known from the start exactly what we wanted. In fact, we used Lisp as a vehicle for exploring instruction sets. The experience has left us convinced of the power of animation as a vehicle for understanding the behavior of parallel systems, and we have decided to include animated simulation in all of our future design aids. The development of expert systems depends on having a computational environment in which you can do experiments. This means a fast development cycle. It means that we have to be able to build big systems, to experiment with them, to roam around in them to understand why they work, what goes wrong, how we can make changes. We don't start out knowing how to build an expert system to help designers. We experiment with it. We try things. We let the system evolve. In a sense, this business of a fast turnaround cycle is very much related to the way we want to experiment with the knowledge in our computer system as well. We don't know what knowledge it takes to design integrated systems effectively. We are experimenting with that. We are creating methodologies. We and our expert circuit designers are creating methodologies. And then we take these methodologies in knowledge bases and run them against problems. Okay? By running them against problems, we can experiment and determine what it is that makes these methodologies powerful, what it is that gives us power in the process of doing design.
These projects have shown how various researchers have applied Interlisp-D's combination of symbolic computing power and flexible interactive environment. While many other projects could have been chosen, these 4 indicate the wide range of topics for which Interlisp-D has proven effective. Over time, this diversity can be expected to grow as it becomes more widely appreciated how Interlisp-D allows one to approach chaos and resolve it into order.